Polynomial lens distortion, accounting for radial lens distortions, nonlinear coordinate space transformations, can be accomplished via polynomial regression. To detect the grid cells, we first threshold and apply a kernel to detect perimeter pixels with respect to a given axis, pairing them into spans, and further relating them into segments. Taking the first y-most pixel per segment, we use that as our entry point to walk the perimeter storing coordinates that we use to emit subgrid lines, with a similar kernel to compress segmentation. For directed hierarchical acyclic graph generation, the lines need to be sorted to match endpoints and direction. The fragmentation is highlighted here by the color. Once sorted, we can score each line with either a 1 or -1 depending on its axis. We sum these scores over a sliding window around the shape. The equidistant scores closest to 0 correspond to windows likely containing the grid cell's corner coordinates. We then sum to find the grid cell center of mass, so that we can measure the distance of each point to find the farthest ones from the center of mass per each window, thus maximizing the value of this function. We then repeat this process for all segment graphs, giving a measure of the distorted coordinates to pair to linear space estimates using optimal transport, which are plugged in to calculate our residuals for our Gauss Newton polynomial regression, giving us everything we need to calculate the radial lens distortion polynomial.